All right. So the next thing, I only have 15 minutes or so. So let me motivate it and then go for the simpler solution. So in this discussion, in the microphone closer. So in this discussion, what I aim to talk about is an issue. Well, technical session always start from an issue. If we don't have an issue, then there's no technical session. So the issue is, let me try to spend only 5 minutes on the background. So the issue was we're making machine learning potential, and we wanted to do it hybrid DFT level, which is one of the strengths of our group. So as you sort of can guess from the directories that I'm making here, this is with Sparta, that we're making PBE0 with van der Waals correction for, in this case, as theoretical. And we have seen some success with lower level DFT, and that's where most people do. And in fact, DPGen, the program that we're running, uses PBE level to develop. So in this case, their development only works for semi-local DFT, not hybrid DFT. And the one, well, they work mostly, but not fully, at least for one espresso wrapper. So when we generate the data, we want to do active learning. There was actually the data that collects from active learning is going to be wrong by a little bit, but we don't want it to be wrong. So we want to fix it. So what is wrong? Let me see. Okay, given the time, so I'm going to keep this very brief. So let me first show you let me just tell you what is wrong. Oh, I don't have 200, but I have 800. So let me show you one example of the output file. So for those of you who have run on special calculations, you know whenever you finish a self-consistent field calculation within the PW program, the total energy is labeled as exclamation mark total energy equal to some number in rubric. So that's the line. And this is the line that DPGen uses a subprogram called dpdata to do data conversion. And then they grab for this line to get the total energy. There's nothing wrong with it for semi-local DFT. But the problem is when it comes to hybrid DFT. You have this expression, but it is not actually the right expression, because in hybrid DFT, you not only get not only trying to get the density self-consistent with the Kongshan Hamiltonian, you also have to get the Kongshan orbital consistent in the Kongshan Hamiltonian, which is used for the exchange calculation. So there is actually a double loop that is involved. At the end, which I'm not going into details until I'm talking to you about the C approach in details, which will take very long time. I would say probably at least 10 hours of discussion, because that's well, first of all, one needs to learn QR factorization in linear algebra. We'll talk about it. So not now, but the actual total energy that we compute is labeled double exclamation mark, and this is not only for C but also for hybrid DFT in general inside one espresso. So obviously, we need this line for the energy part of the data, and it is unfortunately not correctly extracted. It was okay. So let me now go into the part that that was actually used. Okay, so let me go to code. Okay, so I'm going directly to sort of like a quick 30 solution that I sketched with Sparta yesterday, but we are sort of forced to move a little quicker than I typically would do because of the timeline. Okay, so in our group applications, this is the group application that everyone has access to, and it's in your home, linked in your home. In addition to the code templates that you are all quite familiar with now, there are containers which we also use, custom software that contains the compiled Cone Espresso software that you implicitly use, many of you implicitly use. Also, the documentation is a copy there. And your Emacs resurrection installed here. I should delete this. And there is a virtual environment, which we have our custom Python installation in there. Some of you use that for DP data, for format conversion. Some of you use that for NumPy. Some of you use for ASE. Okay, so what I'm going to do is I'm going to make a copy of the virtual environment, which contains the installations. I'm actually not sure if I can do that, so that's why I'm saying this 30. So in a virtual environment, we basically install everything that is needed and in a single folder, so that the Python dependency nightmare is fully contained in a single place. So what I'm going to do here is, well, seems to be pretty big. 1 gig, not too bad. Okay, while it's copying, let me tell you what's going on here. So when you have a Python related package installed in your system, how does it look like? Let me go to the one that we have installed. So this is okay, finally done. So it is the virtual, this is inside the virtual environment, and there is a bin folder that has activate, and that's how you activate your virtual environment. But other than that, virtual environment has a very similar directory structure as you would typically see in Unix-like systems in the root system. So root folder, this is how your root folder look like. They are libraries, binary install packages, and user. And the user also has very similar structures. So those are how you install things. So guess what? In the virtual environment, you get very similar structures for the packages that you need to install. So the bins has, for instance, dpgem, dpdata, and a few other things like lamp. Where's lmp? Oh, it's put in somewhere else. But anyways, so basically those are what you would expect in the bin folder of virtual environment. But Python libraries, Python packages are not only installed in there, their dependencies are installed in library. And you see, depending on the Python versions, Python is a language that is not fully converged yet. So even packages depends on the particular Python version you have. So you will see Python 3.11, you'll see Python 3.6, some of them see Python 2.27 or something. So you have to go into the particular version that you have. Virtual environment are typically made for a particular version. So then this part is simple. Side packages are shared among users. When you do virtual environment, everything installed into side packages. Well, I'm making comments that's a little bit too risky here, but by default install it into that place. And for every packages, we don't have enough time to also show you comparison with the source code, but basically they copy in some very similar structure from the source code. So what we're going to do today is DP data, which is the data conversion part of the deep potential package, as the name suggests. And in this package, they basically do format conversion for many different formats. So you see, you can guess that what we're going to focus on is in here, in Quant Espresso or QE. And you also have probably also have seen DeepMD, which we do conversion for raw format. And you probably also have seen LAMMPS somewhere.
Okay.
Yes, thank you. Okay, so we're going to focus on the QE part, and there are only, well, essentially only two files. This one is for self-consistent field, as the name suggests, and this one is for CP trajectory, so that well, only Teresa has a little experience, but this is the one that we actually use to do conversion. And when we open, this is the Python script, and it's no different from other Python script that we have used before. It's written by a very, very by a very good expert of Python. So you'll see tricks that you can learn from, and some tricks that takes a lot of effort to understand. But we're only going to focus on the one that we are looking for. And I guess you still remember the line that we were looking at, where the total energy is extracted. So this is precisely the expression that when the lines are passed in, we look for if this line has this exclamation mark total energy, and then we're going to split it so that this is a sophisticated split that I happened to explain some time ago. And then we typecast it from a string to a floating point number, and then we do unit conversion, and then that's how they return the total energy. Obviously, this would not work for hybrid DFT because the expression is different. We need a double exclamation mark. Okay, so we have 5 minutes left. So basically what needs to be done is just take this and modify it in such a way that it will work when we have hybrid DFT, and it will fall back to semi-local DFT when we don't have hybrid DFT expression. Can anyone take a guess how this will be done? Add another if. Very good. Well, for the interest of time, in principle, I should give you more iterations in questions how you will write it, so that it will be the best use of everyone's time. But I'm going to show you in the quicker version. So I'm going to go to where we were looking at things, and so this is what they were looking for, and they were going to look for this instead. So let me go to 7. So let me propose the following. You also need to know the number of spaces to be fully right. Oops, come on. Okay. Okay. Can anyone tell me what I did here?
First, we check for double exclamation mark.
That's right.
If it is not there, then we go for single exclamation mark.
That's correct. So this allows you to fall back to second case if the first case doesn't satisfy. And because the structure of this target lines are essentially the same other than the initial part, so the split, so their split is basically first split based on the equal sign, and then find what's after the equal sign, and then split again based on space and find the beginning part. So that's what.
Can we also reverse that, like keeping if single exclamation?
So good question. So
then first do that part, then
Yeah.
Then again calculation is wrong.
Right. So let Barta get it right. Let me just elaborate a little bit. So if you have this, what happens? If you find the line like this, then you won't get to this point. And there's always this line in hybrid DFT calculation, but they don't give you the right number. So you really have to, the order matters here. And this is, I think, the right one, even though I haven't tested. And it's typically good to assume that things are not right in the first place. But this is the what I would sketch out, and then I will start testing based on this. Okay.
In this case, if you don't have double exclamation mark, that only we go for the second.
Right. Because I know people don't have a lot of experience here. So this is how you will see in a C calculation. The self-consistent field ends here. But if you go ahead to see what's there previously, there was a few of these before you can reach the point. It may take a little bit before I find it, the next one. It is because whenever you see this single exclamation mark, you see self-consistency with fixed orbital but a varying density Kongshan Hamiltonian. Why they do that is a little tricky, and it needs a much longer discussion to show you what's going on. In fact, it needs to. I need to tell you what the adaptively compressed exchange operator is. This is the A in the C approach. So it needs a longer discussion, but this is what's happening in Bro stroke. Okay. So time's up, and so I couldn't really show you the test because the test will need a longer version to run through some of the examples and check the extracted numbers to make sure it's actually consistent with what we have in the preprocessed file. But that's how you would change and extend the DP data in order to support hybrid DFT. And the rest, Bart and I checked before, this was the only thing that it gets wrong. So we'll be able to use properly DP data once we correct this part. Yes, Teresa.
While we were doing CF for my calculation, did we do that thing?
No. So very sharp observation, Teresa. So short answer is when we did C calculation, we were not really doing data processing using DP data for energy. We were using DP data only to convert the things from raw format to other formats. So in this regard, I knew this is an issue, but then we didn't use the energy. So we were sort of like, okay, whatever. We have the energy wrong, but we don't use it. If we need to use the energy, then I'll bring this issue up, and it just happens so that Barta needs this now. So we bring this to the group meeting. This is a simple example, so that's why I figured 20 minutes is not too bad of investment here, so that everyone gets to see how you get this kind of problem solved. And it's two-liner. Well, I have to say I haven't tested, so I shouldn't say I fixed it. But if it's successful, then it's a two-liner patch. Probably will commit this to DP data, and people will be happy in the future when they use hybrid DFT. Okay, so I think it was not too bad in terms of the time control. We are right on time. I would say 2 minutes error. Okay, cool. Any questions before we depart?
I have question on my work.
Okay, so then we should continue discussion a little bit, but everyone is welcome to stay. But if you have to do something else,
Third question I have.
Sure question.
Like this for this constraint here we.
And do you want to look? You are already in Zoom, right?
No, I leave that.
Okay, I see. That's fine.
Like we are submitting this for 10 MD segment, right?
That's right.
It will generate 10 MD segment.
So you are doing yes, it will give you 10 empty segments. So Deepa is asking our group script about data generation, and there is a maximum queue.
But
so
it doesn't generate anything. It's like it was running around 3 days now, but it doesn't.
okay.
Should I log in?
Don't worry. So let me stop the meeting and let me give you the
No.